Good morning, friends. We start today's topic or today's lecture again based on the what we discussed last time. That is the nucleus is born, or we know the nucleus. Nucleus is known. From that we are going further and we talk something more. So first let me introduce you a small problem, and that was, say, what is the wavelength of a problem what is the wavelength of 0.186 MeV gamma ray. Emitted from that is not very important. Emitted from, say, some radioactive, say, radium 226. A radium-226 is radioisotope. It emits gamma ray. I have given the energy of the gamma ray emitted from this is 0.186 MeV. What's its wavelength? So you calculate and tell me the answer. What is the wavelength? What is the energy? Energy of gamma ray. You convert, see, energy of gamma ray, that is E gamma ray, is 0.186 into 10 to the power 6 electron volt. That was MeV, so 10 to the power 6 electron volt. This you can convert into joules. Say 0.186 into 10 to the power 6 electron volt multiplied by 1.6 into 10 to the power minus 19. This will be now in joules. So that you can find out, this will be, when you multiply this here, you will get 2.98 into 10 to the power minus 14 joules. So this will be the energy of the gamma ray. Okay, E gamma. Now what is the wavelength? What is the relation of wavelength, energy wavelength? You know, E is equal to h nu. What the frequency and the velocity relation? H c over lambda. So what the lambda? Lambda wavelength is equal to h c over E. I think now you can calculate from this relation. So lambda is hc over E. What is h into c? That you know, the h is the Planck constant. So h is 6.63 into 10 to the power minus 34. That is joules second, 34. And velocity of light 3 into 10 to the power 8. That is the SC, that is the kilometer, divided by centimeter, that is by meter, velocity, and this is the E. E is this thing, 0.186 into 10 to the power 6 into 1.6 into 10 to the power minus 19. So this gives an idea to you, the wavelength of gamma ray of this energy 0.186 MeV emitted from radium-226. You calculate this number, lambda you will find out. The wavelength is lambda is equal to, when you calculate 6.67 into 10 to the power minus 12 meter. So this is the order of wavelength. Just I gave an idea that if the energy is So 0.186 MeV, well, the order of wavelength, this much, 10 to the power minus 12 meter order. So much a small wavelength. So this just a problem I wanted to tell you, the relation between the wavelengths and the energy and the order of wavelengths. Wavelengths of gamma rays are of the order of 10 to the power minus 12 meters. Energy is more, this will be further small. Okay. Now tell me, I raise a question, tell me why systems are stable? Stability, why the nucleus, why the universe, why the elements in the nature are stable. So why they are stable? So what the stability consideration? Stability of elements. Why? Elements means matter. That means matter means actually nucleus. Why the systems are stable? Why the elements are stable? You know, we have nucleus, proton plus neutron, and outside electrons. So this is the whole picture of atom. Atom, we have nucleus, proton plus neutron, outside we have electrons, so this is the whole picture of atom. Well, why the atom is stable? Atom is actually nucleus because electrons are revolving outside in fixed orbit, so they are stable. There is transition only, then the emission of some radiations, some photons. So nucleus is stable. You add on you say the light nucleus, protons are equal to neutrons. But as we go to higher systems, their neutron number increases. As we increase the mass, with the mass increase, neutrons increase. And proton also increase. But remember, as you go to higher systems, there are more and more, you can say, neutron number is large. Neutron number is large in the heavy system, in the heavier system. Neutron number is larger than proton. Well, if this is not so, if proton is also increasing, in nature it is not happening. Why? Because proton is having a repulsion, Coulomb field. So when they are repelling, well, large number of protons will have more and more Coulomb force and system will not be stable. More and more protons will have larger repulsive force. Larger repulsive force means breaking. System will not be stable. system will break. Elements will not be stable. So this is the nature. Nature itself is giving you systems which are having, say, a more number of neutrons. So more number of neutrons give you less repulsive forces. Protons increasing, more repulsive. So neutrons are balancing the, neutrons are keeping the system stable. As repulsive force doesn't increase, repulsive force doesn't increase with the increase of, you say, mass. As the proton we see, as the proton increases, more and more repulsive force, means breaking of possibility increases. So neutrons, heavier system we have more and more neutrons. Heavier system we have more and more neutrons. Means to keep the system stable, what we observe that neutron number increasing and proton number is not increasing as the neutron number increasing. So stability moreover, the increase in mass increases repulsion. So why these systems are stable? To keep the system some forces are required. Some forces means some stronger forces are required. It means the protons here, proton and proton, they are repelling, means they are having force of repulsion, repelling. So it means there must be some force to oppose repulsion of Coulomb forces. There must be some forces to overcome the repulsion. You see, these forces are in between nucleons. You see, nucleon is common name to proton and neutron. Both proton and neutron are called nucleon. So this is a common name. So by nucleon means protons as well as neutrons. So there are some forces between nucleons, means which are called nuclear forces. It means there is something in between nucleons which keeps them bound. That is the binding energy. Binding energy is also, you see, due to the nuclear forces. They are bound systems means, well, to oppose the strong repulsion of the proton, first the systems automatically in the nature, neutron number increases and not the proton number. If proton number also increases, the repulsion force will be much more and systems will not be stable. But other than the increase of neutron number, there are some forces between proton and proton. So this is the force between proton and proton. Force between proton and neutron, and force between neutron and neutron. It means the nuclear forces are special type forces which we do not know so far. What a special type means, they are between the charged particle, also between neutral particle. Charged neutral particle means it is observed that PP forces and Pn forces and Nn forces are nearly equal. They are same. So this is we will discuss separately nuclear forces, but I am just talking about the stability, why the systems are stable. So stability reason is that nucleons, protons or neutrons or proton-neutron, they have, each nucleon, they have some attractive forces which is much stronger than the Coulomb repulsive forces to keep the system stable, and hence the systems remain stable. Well, I can mention here the special characteristic of the forces, that these are short range forces. Short range means these forces are applicable only when the nucleons are very close. If they are far apart, the forces are not there. Means the forces are between neighboring nucleon, not the far away. One nucleon sitting here, one nucleon here. They will not have the nuclear forces. So they are short range. The distance between small means neighboring nucleon, they experience the nuclear forces. So these are, you can say, assumptions, and which will be verified with the help of the experiments, that yes, they are short range forces. All these studies gave, further researchers gave the confirmation that yes, the properties of nuclear forces are verified. So they are short range forces. They are saturated forces, means they are between neighboring nucleon, not with the far away. And the saturation property is due to the binding energy per nucleon is almost constant, around 8 MeV. So this binding energy per nucleon is constant almost for the medium nuclei. So that gives the saturation property. And the saturation property comes from this, and saturation property also comes from the constant nuclear density. Because nuclear density is constant, we have observed. It doesn't depend upon the element to element, just like the physical density of the system. So constant nuclear density, that is the size of the nucleus increases with the number of nucleons, with the mass. As mass increases, volume also increases accordingly, so that mass upon volume remains constant. So that is the constant nuclear density also gives the saturation. Density is not increasing, density is not decreasing. Density increasing, then it will not be saturation. So saturation nuclear forces due to the binding energy constant, due to the nuclear density constant. Nuclear forces are short range, they are saturated. They are also, you see, charge independent. The meaning of charge independence is that they are same forces between proton-proton and neutron-neutron or proton-neutron. They don't depend on charge. Whether the nucleon is neutral, that is the neutron, or whether the nucleons are protons. So the forces between proton-proton, forces between proton-neutron, forces between neutron-neutron, all are same, similar. So they are charge independent. Short range, saturated, charge independent. So these are, you see, main characteristics of the nuclear forces. We will discuss details also after, maybe when we discuss nuclear forces, but not now, after. So these are main characteristics of nuclear forces. Due to these nuclear forces, systems are stable. So stability of systems is due to the nuclear forces. Unaided by any external agency. It means we are not supplying any energy, we are not heating, we are not doing anything. They emit some radiations naturally. That is called natural emission of radiations or natural radioactivity. Radioactivity can be two types. One is natural, other is man-made also by some nuclear reactions. But I am talking at this time about natural radioactivity. It is observed that some elements or of different materials, that they are called isotopes, of having same charge, different masses, they are isotopes of same element, and they emit some radiations. It was found that they emit alpha particles, they emit beta particles, they emit gamma. These are the alpha, beta, gamma, three radiations. They were given name, natural emission of these radiations from any element. Later on it was found that by studying the properties of these radiations, the alpha particle is nothing else but twice helium-4 nucleus from which 2 electrons have been removed. So it becomes doubly charged. Alpha particle has got 2 units of positive charge. So Z is 2 and mass is 4, helium-4. So alpha particle is like that. And beta particle is also beta positive and also beta negative. Means it is just like electron, positive electron and negative electron. Beta particle is just equivalent to electron. Positive electron is called positron, and this is the electron, negative. So electron, and this is the antiparticle of electron, this positron. So beta positive is the electron, positive electron. Its charge is same as the electron but positive. Its mass is same as the electron mass. Electron charge is negative and mass both are same. Gamma radiations are electromagnetic waves, you can say, just like waves, electromagnetic radiation. These are particles, you can say these are the gamma rays are waves, electromagnetic waves, electromagnetic radiation. This has energy, E gamma is equal to h nu is equal to hc over lambda. So this is wave generated by electromagnetic origin. So these radiations are automatically coming out from the elements, and those elements which emit these radiations are called radioactive. Radioactivity, you see, is also having some, is defined in terms of its units, etc. How it is measured, what the units, how they are measured, how they are defined. So you see, the radioactivity is measured in terms of, is defined as one becquerel. Becquerel name, 1 becquerel of radioactivity is equivalent to 1 disintegration which is per second. In 1 second, if one nucleus disintegrates, decays to the other, that activity of that system, that matter is called 1 becquerel. 1 becquerel means 1 disintegration in 1 second. So that is the activity. Activity means disintegration rate. So that is the disintegration 1 per second is called 1 becquerel. Just like that, we have another unit is called 1 Ci, that is 1 curie. 1 curie means 1 curie is definition, some amount of the material. Here it is 3.7 into 10 to power 10 disintegrations per second. If any element having so many disintegrations per second, that activity is called 1 curie, and the name of curie. The definition, the activity means disintegration rate. That is the activity of element. Activity means disintegration. Disintegration rate. So these disintegrations definitions are Curie and Becquerel. Then there is another one, Rutherford probably, 10 to the power 6. 1 Rutherford unit is, this is defined as 10 to the power 6. 10 to the power 6 disintegrations per second. So this is another definition. 1 Rutherford activity is called 10 to the power 6 disintegrations per second. So activity, you see, activity means how many nuclei are changing to other system per second, per unit time. It is found that if d and dt is the rate of disintegrations, rate of disintegration, means d and dt means dn is the change of nuclei in dt times. So d and dt means disintegration rate per unit time. This is proportional to n, means what the number of radioactive nuclei, where n is N is radioactive nuclei number. N. In fact, this is minus because mathematically dn dt is the increment. Dn is the increment. Dn is mathematically, but here it is a decrease. Rate of decrease, rate of disintegration. So dn dt, to make it negative, we put this minus here. Dn dt is proportional to minus n because it is the mathematically dn is always increment. We want to make it decrease. So that is dn dt we write proportional to minus n, or we write that dn dt is equal to minus n and lambda, where lambda is constant of proportionality. We convert proportionality into equality. dn dt is equal to minus n lambda. From this differential equation, you can get a relation like just integrate and you can get n is equal to n naught e to power minus lambda t, where at t is equal to 0, n is equal to n naught. Means n naught is the initial number of radioactive nuclei at t is equal to 0. So when you integrate this and you have just to find out the constant of integration by putting the condition t is equal to 0, n is equal to n naught. You get this equation dn dt is given by that n is n at any time. N is a number of nuclei at any time, radioactive nuclei, and n naught is at t equal to 0. So this equation gives you that how the nuclei are decreasing, n naught initial and exponential decay. This gives the exponential decrement of the system, means it's starting like this. And that is the time as time increasing, t. And this is the activity means n, how the n is decreasing. So this equation n equal to n naught e to power minus lambda t is plotted here with time, that this is called exponential decay. This is the nature. This is called law of decay. Also, we can say natural decay, law of decay. That n is changing with time by this equation, where n naught is the number of radioactive nuclei at initial time, means t is equal to 0. From there we started, and lambda is called decay constant. Lambda is decay constant. Also you can call this disintegrations. From the equation that you see dn dt is equal to minus n lambda. Well, lambda is dn dt upon n. So disintegrations per unit time. Decay constant. Disintegration rate, you can say. Disintegration rate. Decay constant. Actually, more proper name is decay constant. Lambda is decay per unit time. So, and what n lambda? You see, n lambda is activity, it is called activity. N lambda is called activity, that is dn dt. This is activity, disintegration rate. N lambda is activity, that is disintegration. So activity is given by N lambda. Lambda decay constant. N is the number of radioactive nuclei any time. Now you can see that from this equation, N is equal to N naught e to power minus lambda t. We can define some time from this equation. One is defined as the half-life of the radioactive material. Means the time after which the activity becomes half. So that is N, or the number of radioactive nuclei. From this, suppose N is equal to N naught by 2, half of the initial. You put this here, N equal to N naught by 2. Here, N naught e to power minus lambda, and this T we write by T half-life. So the time after which the number of radioactive nuclei is half of the initial number. From this you can get the value of T half. You just find out, take the log and find out this, the value N naught cancels. So you can get just so from this relation, N naught cancels, so you have e to power minus lambda T half is equal to 1 by 2 N naught cancel, e to power minus. So that is you get here. Or e to power lambda T half is equal to 2. From this you can find out that lambda T half is equal to ln natural, take log of 2, or T half is equal to ln natural log of 2 divided by the lambda. Log of 2, natural log of 2 on the base of E, this is simply T half 0.693 divided by lambda. So this time is called half-life. The time after which the activity, the number of radioactive nucleus becomes half, that is 0.693 upon lambda, or lambda is equal to 0.693 upon T half. Both relations. The decay constant is related with the half-life by this equation. A half-life means a time after which the radioactive nuclei becomes half of the initial, and that is 0.693 upon lambda. From this you can find out more and more time when it becomes quarter, when it becomes 1 by 8 like that. But main important property of radioactive nuclei is the half-life. Each and every isotope radioactive element is given half-life. In the tables you can find in the books that they write half-life. Half-life of this element is there. Half-life, each element, radioactive element has got half-life. So one is half-life, important term. Another term is mean life. Mean life. So what is the mean life? You see, some radioactive nuclei have 0 time, means just the system is formed, some decays. Some decay after a few seconds, some decay after a few seconds, some more decay after a few seconds. Some after half-life, still half are remaining there. Then they are decaying. So it means different nuclei are decaying with the time, exponential decay. Even at the T is very large, some nuclei is still remaining there. Means they have infinite lifetime, you can say. So they don't have, all nuclei are not decaying at one time. Some are still remaining. So we have a mean life, means lifetime from 0 to infinity. And that is we get the, from integration, from that equation we write dn over n is equal to minus lambda dt. If we write this equation, this is from n0 to n, and this is from 0 to t. At t is equal to 0, number of nuclei is n0. At any time t, number of nuclei are n. So dn over n, from the same equation, dn over dt is equal to minus n lambda. We can get this thing. And to get the average life, we integrate this expression over the limit from 0 to t. Integrate this thing, because some has got lifetime 0, some has got lifetime infinite. So from this relation we define, and we get this is the, from this relation we get this relation. This is the outcome of this relation. And we see after half-life, as we have, say, yes, mean life also you can calculate. In fact, you can get mean life from the formula. Mean life we write by symbol tau. Tau is the mean life, that is the sum has got lifetime n0 e to power minus lambda t, this into dt. In dt time they are decaying, n is decaying, and then this integrate from 0 to infinity and divide by the number of radioactive nuclei n0. So this becomes the total lifetime, total time of all from 0 to infinity, and number of radioactive nuclei. So you divide this total time by the number of nuclei, this gives the mean life of the system. So you find out this, you integrate this expression, 0 to infinity, n0 e to power, this is n, number of nuclei n decays it in time dt. So dt into n. So many nuclei have decayed in time dt. So we find out how many nuclei, 0 to infinity time, total number of, that is the lifetime, and divide by the number of nuclei n0. So this gives the mean life. You solve this, find out this, you will get the relation just like tau is equal to 1 over lambda. That is the mean life. Half-life is here, this, and here mean life. This is the half-life and this is the mean life. Mean life from this relation will be tau is equal to 1 over lambda. So these are two terms for radioactive systems. One is half-life, other is mean life. Half-life is just given, written in the books, in the table of each element. Mean life is not mentioned. So half-life is more important because it is the important parameter for radioactive elements. Now, we can have some, I have one problem. You can say the half-life of AU gold, the half-life of AU 197. Half-life of A197 is 2.7 days. calculate decay constant average life means mean life, that is mean. Average life so half-life is given. Find out lambda, find out mean life. So you can get this. You see, T half, the half-life of calculate decay constant average life, the activity of 1 milligram, the activity of 1 milligram of AU-197 atomic weight A is equal to 198. So T half you can find first T half. T half is ln2 divided by lambda. ln2 we know is 0.693 divided by lambda. So half-life is given here, 2.7 days. You put this here, you can find out 2.7 days is this half-life. So 2.7 days is 0.693 by lambda. You can find out lambda. That is lambda equal to 0.693, 2.7 days convert into second. So 2.7 days, 24 hours, and 1 hour is 60 minutes and then 60 seconds. So this will be proper units. So this will be, you can find out 2.9 into 10 to the power minus 6 lambda. And the lambda unit is, lambda is having 1 over time. So second inverse. So this is the value of lambda, 2.9 into 10 to the power minus 6 second inverse from this simple. And now we have said tau, this was the lambda. So find out the calculate decay constant and average life. So average life means tau, mean life, 1 over lambda. So 1 over lambda means 1 over 2.9 into 10 to the power minus 6. So find out this. So this will be 3.9 days. Now you find out activity of 1 milligram of this. So this activity of 1 milligram, how much is the activity of 1 milligram? How to calculate this? This is half-life and mean life. Now we have to see the activity of 1 milligram of gold. What is the activity of 1 milligram of gold? Where A is 198. So now we will calculate the activity of 1 milligram of the gold. How to calculate? You see the activity of 1 milligram of gold. You see N is equal to, the activity is divided by A, activity A is lambda into N. Minus sign just gives the decrement. So lambda N. And the lambda we have calculated, so we know that activity, and N is the number of nuclei, lambda we know. So activity we know, we find out now N is equal to Yes, A upon lambda. So, how to get? N is equal to 6 into 10 to the power 23. That is Avogadro number. You want to get the number of nuclei in one atomic weight and then in 1 milligram. So this into 1 milligram divided by the atomic weight 198. In 198, this much number of nuclei. In 1 milligram, how many nuclei? That is N. So that you can calculate. Number of nuclei is how much? 3.02 into 10 to the power 18. So in 1 milligram, this is number of nuclei. In 1 milligram of AU, these are the number of nuclei N. So many nuclei are in 1 milligram of gold. This gives you the value of activity. Activity A is equal to lambda N, and lambda we have already calculated. That was how much? Yeah, earlier we got the lambda. Lambda was 2.9. 2.9 into 10 to the power minus 6. So 2.9 into 10 to the power minus 6. This was lambda. And lambda into N. N is 3.02 into 10 to the power 18. So this becomes activity. Activity is, you can find out this, multiply this. So you will get activity equal to 8.8 10 to the power 12 disintegrations per second, of course, activity. And then you can get this in terms of other units also. That means you divide this by, say, in terms of Curie. How many Curies? You know, 1 Curie is equal to 3.7 into 10 to the power 10 disintegration. So you can convert this into Curie. You divide by this, you will get this activity as 8.8 into 10 to the power 12 divided by 3.7 into 10 to the power 10. This becomes Curie. So the activity in terms of Curie, just divide this. You will get 240 Curie. So activity of 1 milligram of gold is 240 Curie. So this is just idea of half-life, mean life, activity, radioactivity, and something about the radioactivity. We will discuss more, or we will do more problems maybe when we meet next time. So I will stop at this place.